Hello students, welcome back to Easy BTech channel and you are listening to the course of Signals and Systems. Okay, so if you remember, we are in first chapter and we are looking at the topic of classification of signals. In this lecture, we will look at another classification, which is energy of signals. Okay, so how do you define energy of a signal? So let us look at that for both continuous time case and discrete time case. So first let us look at continuous time case. For a continuous time signal x of t, energy is defined as ex. Okay, that is a notation for energy, which is equal to integral minus infinity to infinity x of t times conjugation of x of t times dt. Note that here x of t can be complex, and then the reason we have to take conjugation of the signal. Okay, this is a way how we define the energy of a continuous time case. And even for discrete time case, we will follow the same rule. What is that? Energy of a signal ex is equal to signal is x of n. For that signal x of n, energy is defined as ex equal to summation n equal to minus infinity to infinity x of n times conjugation of x of n. Again, we assume that in general x of n can be complex, but if the energy of the signal is finite, okay, so mathematically we represent it as 0 less than ex less than infinite. So if you see this condition, it means that energy of the signal is finite. Then what do we say? We say that that particular signal is energy signal. Okay, if the energy of a signal is finite, then we say that signal to be an energy signal. This is valid for both continuous time case and discrete time case. Okay, so what happens if the signal x of t is real? So in previous definition, we assume that in general x of t can be complex, but what happens if the signal is complex? This conjugation of x of t is same as x of t, and hence what happens, you get x of t times x of t, which turns out to be x square of t. So that is, if the signal x of t is real, then energy of the signal turns out to be, for continuous time case, integral minus infinity to infinity x square of t dt. Even for discrete time case, the same rule applies. So energy is defined as summation n equal to minus infinity to infinity x square of n. Sorry. Yes, but what happens if the signal is complex? This result can be directly obtained from the definition of the energy itself. So if you assume that this is some complex number z, so this fellow would be z star. So what happens if you multiply a complex number with its conjugate? You get the absolute value of that complex number whole square, and that's what we have got here. So if x of t is complex, ex turns out to be integral minus infinity to infinity sorry, modulus of x of t whole square dt. Same rule applies for discrete time case. If x of n is complex, then energy would be equal to summation n equal to minus infinity to infinity modulus of x of n whole square. Okay, so now let us look at a few examples and infer few more observations. Okay, so for the given signal x1 of t here, we are asked to find the energy. So let us call that energy to be even. Actually, integral should be from minus infinity to infinity, but the signal exists only from minus 1 to 1. And because the signal is real, so why do I say signal is real here? Because the amplitude of the signal for all values of time is a real number, and hence which equation we can use? Integral minus 1 to 1 x1 square of t. No need of putting modulus. Even if you put modulus also, there is no problem. So you will get x1 square of t dt. So that would be equal to integral minus 1 to 1 square dt, which simplifies to 2. Because this fellow is less than infinity, our signal x1 of t is energy signal. Okay, because the energy of the signal is finite, we say that our signal x1 of t is an energy signal. Now in the second example, let us shift the signal and see what happens. So we will take this signal x2 of t, which is nothing but our x1 of t shifted to the right by 2 units. Let us try to find out the energy of this signal. Let us call that to be E2. And because this signal is also real, we can use the first equation, and the integral limits actually should be from minus infinity to infinity, but see this signal exists only from 1 to 3, and we will say x2 square of t dt. Okay, so that would be equal to integral 1 to 3 x between 1 and 3 amplitude of signal is 1, and you get again this would be equal to 2 units. Okay, and because this is again less than infinity, we say that x2 of t is also energy signal. Okay, x2 of t is also energy signal. Okay, but what is that you observe? Even if you shift the signal, the energy of the signal is not going to change. Okay, so what do we see? Shifting operation. Okay, so shifting operation does not affect the energy of the signal. Okay, so shifting operation does not affect energy of the signal. So that is good inference which we have got. Does not affect the energy of the signal. Now, as a third example, what we will do, we will do the time reversal of x2 of t. Means what? You just rotate the signal along y-axis. Okay, so the signal will look like this, right? So if you look at x3 of t and x2 of t, what is that you observe? Our x3 of t is nothing but time reversed version of x2 of t, and again the amplitude of the signal is always real. So what will happen? Our E3, which is energy of this signal, would be equal to integral minus 3 to minus 1. You'll get to 1 square dt, which is equal to 2, and again this is less than infinity, and hence what do we say? x3 of t is also energy signal. Okay, x3 of t is also energy signal. But what is important thing that you observed? Time reversal operation also does not affect the energy of the signal. Okay, so time reversal operation. Okay, so time reversal operation does not affect. Okay, so does not affect energy. So okay, does not affect the energy of the signal. So two things we have observed from the previous example. We have observed that time shifting operation does not affect the signal, and time reversal operation also does not affect the signal. So that is very important. Okay, right. So for example, we have a signal x of t with energy E, let us say. So now we are asked to find the energy of, let us say, x of minus t plus 3. Okay, what is the energy of this signal? So this plus 3 corresponds to time shifting, so that fellow has no impact on the energy. Minus t corresponds to time reversal operation, that also doesn't have any impact on the energy. So what will happen? Because it is time shifting and time reversal, both operation does not affect the energy of the signal, and hence energy of x of minus t plus 3 would be again E. Okay, so that is just for example. Okay, right, we will see more formally in the last slide. Okay, next question, we are asked to find the energy of this signal, which is exponentially decaying function from 0 to infinity. Okay, so what will be the energy of this signal? E4. So integral limits actually should be from minus infinity to infinity, but the signal exists only from 0 to infinity. So you have e power minus at. You have to take the square. Here we assume that a is real, and hence you get this equation. So you will get integral 0 to infinity. This fellow would be e power minus 2at dt. So that you can easily see that simplifies to 1 by 2a, and because this flow is less than infinity, x4 of t is also energy signal. Okay, so x4 of t is energy signal. Okay, right, next, so we'll take the next example, which is unit step function. So for this signal e5, which is energy of the signal xy of t, would be integral 0 to infinity, because the signal exists only from 0 to infinity. We should take the limits from 0 to infinity. You get to 1 square dt, so which again would be equal to infinity. So this implies our signal x5 of t is not energy signal. Okay, so this fellow is not an energy signal. Why? When do you say a signal is energy signal? If its energy is finite, then we say that signal to be energy signal. If the signal becomes infinite, we will say that signal to be not an energy signal. Okay, right. So next we'll take one example which has amplitude of the signal to be complex, and hence we should be careful in evaluating energy of this signal because the amplitude of the signal is complex. So from -2 to 0, the amplitude of the signal is 2z. So what will happen? The integral limits will be from -2 to 0. Because the amplitude of the signal is complex, we should take modulus. Okay, modulus of 2j whole square plus between 0 to 2 amplitude is 0, and hence we'll write 0. And again from 1 to 2 amplitude is 1 minus j. We should take modulus whole square dt. Okay, so that simplifies 2. So this would be how much here? So this would be 4 times 2. Correct. So this is 4 times 2. That is the first term plus 0 plus, so this is, sorry, the integral limits are 2 to 4, right? So this integral limits are 2 to 4. Okay, so this would be equal to, so 1 minus j modulus is root 2. Root 2 whole square is 2 times 2. So that turns out to be 8 plus 4, which is equal to 12 units, and this fellow is again less than infinity, and hence what do we say? X6 of t is again energy signal. Okay, x6 of t is energy signal. So in that way, if the signal amplitude is complex, we should make sure that we take the modulus of that amplitude whole square and then do the integration. Okay, so now let us try to evaluate energy of this generic signal. Okay, so we want to find the energy of this signal y of t, which is defined as c times x of at plus b. So let us call that to be ey, which is nothing but integral minus infinity to infinity y of t multiplied with y star of t dt. Okay, so what is given? Energy of the signal x of t is given to be ex, let's assume, and we are asked to find the energy of y of t. Okay, so energy of y of t is defined as integral minus infinity to infinity y of t times y star of t dt. So let us substitute what is y of t. We get integral minus infinity to infinity c times x of a t plus b multiplied with y star. So c can be complex, and hence we should take c star, and the signal x also can be complex, and hence we should take x star of a t plus b dt. So everything is multiplication here, and then c times c star would be modulus of c whole square. Let us keep that out because integration is with respect to t, and hence modulus of c is a constant. We can bring it out. So you will get integral minus infinity to infinity x of a t plus b is like z1, that is some complex number z1. X star of a t plus b is nothing but that z1 star. So z1 times z1 star would be modulus of z1 whole square, which is nothing but x of a t plus b whole square dt. Okay, now let us do the change of variables, which is at plus b equal to, let's call that some tau. Okay, so let at plus b equal to tau. So this implies what? We get dt to be equal to d tau by a. Correct. So if you differentiate, b is gone, so we'll get dt to be equal to d tau by a. So let us substitute in this equation. So what do we get? We get ey. Correct. So we get ey to be equal to modulus of c whole square. That dt is replaced with d tau by a, and hence you'll get by a. So if t varies from minus infinity to infinity, tau also will vary from minus infinity to plus infinity. So you get modulus of x of tau whole square d tau. Okay, so modulus of c whole square by a, integral minus infinity to infinity modulus of x of tau whole square by a. Okay, so note that a can be negative also, but we know that if a is negative, that is nothing but time reversal operation. So time reversal operation does not impact the energy of the signal. Okay, so we'll write down that as time reversal. Okay, so time reversal means what? Has no impact on energy. Okay, as time reversal has no impact on energy. So we can replace Ey with equal to how much? Modulus of c whole square by modulus of a. If a is negative also, it doesn't have impact, and hence we'll take the modulus of a. Integral minus infinity to infinity mod x of tau whole square dt is nothing but our energy of the signal x of t. So if x of t has energy to be equal to Ex, okay, then y of t equal to c times x of a t plus b. So that fellow will have modulus of c whole square by modulus of a times Ex as the energy of the signal. So this is a important and nice result. So note that the time shifting operation doesn't have any impact on the energy. Okay, so yes, if a is just -1, we call it as a time reversal, and if a is not -1, and if a is some fraction or some number which is greater than 1, then we say that it is the time scaling operation. So time scaling operation will have an impact, but time reversal will not have any impact on the energy of the signal, and hence we should take modulus of a here. Okay, right. So next, let us move on to discrete time case. So we are asked to find the energy of this signal. So what will happen? So let us again call that to be even, because amplitude of the signal is real. What is that we have to do? We should take summation n equal to minus infinity to infinity x1 square of n as the energy of the signal, but this signal exists only from -2 to 2, and hence at it is enough that we take only these samples. At -2, what's amplitude is 1, so we have to square that. At -1, amplitude is 2, we have to square that. At 0, amplitude is 3, we have to square that, and so on. At 1, amplitude is 2, we have to square. At 2, amplitude is 1, we have to square, and for all other values the amplitudes are zeros, and hence this turns out to be how much here? This is 1 plus 4 plus 9 plus 4 plus 1. So this should be equal to, so 9, 8, 4 plus 4 is 8, 9, 10, 10 plus 9 is 19. And because this fellow is less than infinity, what do we say? X1 of n is energy signal. Why? Because the energy of the signal is finite. It is less than infinity, and hence we say that x1 of n is energy signal. And same rule applies. What is that? If you shift the signal, energy is not going to change. If you rotate the signal, energy is also not going to change. So for both continuous time and discrete time cases, the same result holds. Okay, right. Next, we are asked to find the energy of this exponentially decaying function. Okay, so at 0, amplitude is 1. At 1, amplitude is a. At 2, amplitude is a square. At 3, amplitude of the signal is a cube, and so on. So we are asked to find the energy of the signal. So let us call that to be E2, and again that would be equal to n equal to minus infinity to infinity. And because the signal is real, we will take just the second equation or first equation, which is nothing but x2 square of n. Okay, so what will happen? So you have to square and add, but the signal starts only at 0. At 0, what is the value? It is 1. And at 1, what is the value? It is a. You have to square it, so you'll get 1 plus a, because you have to square the samples. So at 2, amplitude of the signal is a square, and square that, so that will give you a 4, and so on. At 3, it is a cube, square it, it will become a power 6, and so on. Okay, in that way we will get the energy of the signal. So this is a geometric progression, and we can easily see that that is nothing but 1 by 1 minus a square, because a is a finite number. 1 by 1 minus a square is also finite number, and hence what do we say? Our signal x2 of n is energy signal. Okay, x2 of n is energy signal. Okay, so next example we will take x3 of n, which is given by this. So that would be given by E3 equal to, again we take summation n equal to minus infinity to infinity x cube square of n. Because the signal is real, we will take this equation. So that turns out to be how much here? At 0, from 0 to infinity, all the values are 1. So we'll get 1 square plus 1 square and so on up to infinity. So that simplifies to infinity. And hence what do we say? We say that the signal x3 of n is not energy signal. X3 of n is not an energy signal. Okay, right. Next, we are asked to, last example, we are asked to find the energy of this fourth signal, which is given by this. So what will happen? This would be equal to E4. Because the signal is complex, we have to take the absolute value of that, square it and add them. So we'll get module at -1, at amplitude is 2 plus j. So we'll get modulus of 2 plus j whole square, plus at 3 it is a real number. Whether you take modulus or not, it has no impact. So we'll get 3 square. At 2 it is 1 plus j, so we'll get 1 plus j whole square, and all other values are zeros. So that should be equal to, this would be equal to how much? So root of 4 plus 1, which is 5. Root of 5 whole square is 5, plus 3 square is 9, plus this is 2. So finally this would be equal to 9 plus 7, which is 16. And because this is less than infinity, what do we say? Because energy of the signal is finite, we say that the signal x4 of n is energy signal. Okay, x4 of n is energy signal. Okay, so in that way we can check whether a given signal is energy signal or not, whether it is for discrete time case or continuous time case. Okay, I'll stop this and we will continue with the next topic in the next class. Thank you.